Today we are looking at tutorial 5a. Consider the following income model for a two-sector economy. Y is equal to C plus I, which represents the total income within the economy. C is equal to C0 plus BY, which is equal to total consumption. And I is equal to I0 plus AY, which is total investment within the economy. And A and B are both greater than 0. Write this in the form of R multiplied by the vector y is equal to the vector y naught, with the vector y equaling the variables y, c, and I. Determine the condition on A and B for the inverse of R to exist and find the equilibrium outcomes as a function of the base levels of the vector y naught. Okay, I'm first going to just rewrite the three equations we are given. So y is equal to c plus I, c is equal to c naught plus by, I is equal to I naught plus a y. We want it in the form of some matrix called R multiplied by y c I is going to be equal to y naught, c naught, and then I naught. And that's what this is telling us. So now if I rewrite these three equations, so we have something that looks like this form, where we get y minus c minus I is equal to 0, minus by minus plus c is equal to c naught, and then minus a y plus I is equal to I naught. So now if we take all the coefficients of y, c, and I, we will get the matrix R. So this is our matrix R. And that is now our equation. If we just wanted to quickly check this, if we took this row and multiplied it by this column, we would get 1 minus c minus I, which is what we have over here. And if we multiplied this row by the column, we'd get minus by plus c, which is what we have. And then lastly, minus a plus I. Cool. Another thing that we can notice is that this first equation is equal to 0, so we can replace this with a 0. Now, if we just fill that in over here. Cool. Next part of the question is determine the condition on A and B for R1 to exist. So R1 is the inverse matrix. For the inverse matrix to exist, the det of R cannot be equal to 0. So if we begin by working out the determinant of 0, I choose 1 and then work out the matrix of minor, the determinant of the matrix of minor, which is 1, 0, 0, 1. And then I choose minus 1 and then write down the determinant of that matrix of minor, which is minus b, 0, minus a, 1. And then finally minus 1 with the matrix of minor being minus b, 1, minus a, 0. So the determinant of this matrix is just 1. The determinant of this matrix is just minus b. And the determinant of this matrix is just a. So we get 1 minus b minus a. Now, if we make 1 minus b minus a equal to 0, there won't be a determinant. If we make this equal to 0, then we won't be able to find, if we make this equal to 0, then the inverse wouldn't exist. If I now rearrange this, I get 1 is equal to a plus b. So essentially, when a plus b is equal to 1, R1, or R, the inverse of R, won't exist. So the conditions for on A and B for R1 to exist would be that a plus b is not equal to 1, R1 will exist, if that's true. Cool, hopefully that makes sense. So the condition on A and B is that A plus B cannot be equal to 1. And now we need to find the equilibrium outcomes as a function of the base levels of y0. Okay, in order to do this, we rearrange this equation, and we now solve for y, c, and I. In order to do that, we form the inverse of r and multiply that with y, o, c, o, and I, o. So what we first have to do is find the inverse of r. So our matrix R was 1, minus 1, minus 1. If we now work out the determinant of R, it was 1 minus B minus A. And the second step to work out the inverse of R would be to form the matrix of minus. So R matrix of minus. To do that, if I pick 1, the matrix of minor would be what's left behind when I remove the row and column that 1 exists in. So that's 1, 0, 0, 1, and I now find the determinant of this matrix, which is just 1. If I choose minus 1, then the matrix of minor would be minus B, 0, minus A, 1. The determinant of that matrix is just minus B. If I choose minus 1, then the determinant of the matrix of minor is just A. If I choose minus B, then the determinant of the matrix of minor is minus 1. When I choose 1, it is 1 minus A. When I choose 0, it is minus A. When I choose minus A over here, the determinant of the matrix of minor is 1. When I choose 0, it is minus B. And when I choose 1 over here, it is 1 minus B. So that's the matrix of minors. Now I need to form from this the matrix of cofactors. So that's just me using this matrix and changing the signs of the matrix of minors matrix. So 1 stays the same, minus B now turns positive, A stays the same, minus 1 turns positive, minus A turns positive, this B turns positive, and 1 minus B stays the same. And then finally, we transpose this matrix and we multiply it by 1 over the det. So 1 over the determinant is 1 over 1 minus B minus A. And this matrix transposed would be 1, 1, 1, B, 1 minus A, B, and A, 1 minus B. Cool. Now, going back to what we had before, to find these values, we need to do the inverse of R multiplied by 0, C0, I0. So now if I fill in what the inverse matrix is, we get this. If I now multiply the two matrices, I get C0 plus I0, 1 minus A, multiplied by C0 plus B I0, and AC0 plus 1 minus B I0, which is equal to Y, C, and I. So now I can say Y is equal to C0 plus I0 all over 1 minus B minus A. C is equal to 1 minus A C0 plus B I0 all over 1 minus B minus A. And then I is equal to AC0 plus 1 minus B I0 all over 1 minus B minus A. So those are our solutions, or the equilibrium outcomes. So if we just fill that in now, we would have this. Cool. So that's part A done. Part B, now suppose we model the dynamics of the approach to the economic equilibrium as vector y brackets t plus 1 minus vector y t is equal to gamma brackets r multiplied by vector y t minus vector y naught. Close brackets with gamma is a real number. Find the stationary state, the Jacobian matrix J, in this difference equation when the vector y t is equal to the vector y s plus delta t, the vector delta t. Right. Let's just have a quick think about what this is actually saying. So what we have here is previously we solved a system of equations which was the matrix R multiplied by the vector y was equal to the vector y naught. And what we did here, we found the steady state. Here, what we are doing is, here we are looking at the transition dynamics, which just means how fast or just how does the economy move towards a steady state. Because of course the economy isn't always at its steady state, it has to move towards it over time. A model which links to transition dynamics is the solo growth model, which is a long run model which tries to explain economic growth through capital accumulation. So let's say we had some level of output in the economy, which slowly starts to plateau off after there's a high amount of capital in the economy. And let's say there is some level of investment, which is going to be some factor of output. So let's put investment over here. And let's say there's also capital depreciation, which happens, which is going to be some level of capital. So some of the capital every year will depreciate. Now, this model explains economic growth through capital accumulation, and we see that when investment is equal to depreciation, which would be this point over here, we have a steady state. Okay. Now let's say that the economy is at this level of investment. At this level of investment is greater than depreciation, which means that capital will be able to accumulate as the level of investment is greater than the level of capital depreciation. As a result, over the years, we will slowly move this way. As more capital is being accumulated, capital is going to increase. And then we will reach this point over here, which is where the level of capital investment is equal to the level of capital depreciation. At this point, if we continue going on, we see that depreciation becomes greater than investment, which means that capital accumulation begins to fall because the rate of depreciation is higher than how much we're investing in capital. As a result, we would start moving backwards back to this steady state. So essentially, it doesn't matter where you are on this investment curve, you always move towards this steady state. It just depends upon how fast the economy is able to move towards this steady state. These arrows that I've drawn is what is known as transition dynamics. So that's essentially what this difference equation is showing. If we have some year, if we add 1 to that year, how far away are we from the steady state or the equilibrium, essentially, is what this is saying. So what we need to do is find a steady state, ys, the Jacobian matrix. If we begin by finding the steady state is when this, so next year, will be equal to the initial year. For that to be the case, if I move this to the other side, we will need to have this equation equal to 0. This equation equals 0 when this part is equal to 0. So gamma brackets r dot yt minus y0 is equal to 0. Now, if we get rid of the gamma, or divide by the gamma, we get r multiplied by yt minus y0 is equal to 0. Moving y0 to the other side, we have r yt is equal to y0. So you might notice that this is very similar to what we solved before, and it is in fact the same thing. So what ends up happening is that the stationary state is the exact same equilibrium that we found before. So we can write down the same answers: CO plus IO, 1 minus B minus A, 1 minus A, CO plus BIO over 1 minus B minus A, and ACO plus 1 minus BIO all over 1 minus B minus A. Hopefully you can all see that. Now we need to find the Jacobian matrix J in delta t plus 1 minus delta t is equal to delta t multiplied by the Jacobian. If I just rewrite that over here, we have yt plus 1 minus yt is equal to gamma r multiplied by yt minus y0. And we are also given the equation yt is equal to ys, which is our steady or stationary state, plus delta t, which just stands for a very small change. So yt is equal to the steady state plus a very small change. Okay, if we now sub this equation into here, we get ys plus delta t plus 1 minus ys minus delta t is equal to gamma r ys plus r delta t minus y0. Okay, so we can see that these two get cancelled out. So we are left with delta t plus 1 minus delta t is equal to lambda r ys minus y0 plus r delta t. Okay, if we look at this, this is saying r, the matrix R multiplied by the steady state or the stationary state minus y naught. So if you notice, this is what we solved in part A, because in part A we solved R multiplied by y, the vector y is equal to y naught. If we now move y naught to the other side, we get this is equal to 0, hence this is also equal to 0. And the stationary state is the exact same as our equilibrium outcome, hence why these two are the exact same thing. So we know that this turns into a 0. So now we're left with delta t plus 1 minus delta t is equal to gamma r delta t. So we have this. If I now write down what's given in the question, which was delta t plus 1 minus delta t is equal to delta t multiplied by the Jacobian. If we just compare these two, we can see that the Jacobian must be equal to gamma r. So the Jacobian is then gamma, the matrix R, which was 1 minus 1 minus 1, which was this. Multiplying this by gamma, we get gamma minus gamma minus gamma minus gamma b, gamma 0 minus gamma a, 0, gamma. So this is our Jacobian. If I now just write that over here. Cool. So we've found the stationary state and we've found the Jacobian matrix. Cool. Moving on. Analyze whether there are conditions on the values of gamma A and B for the stationary state to be stable, and whether there are values of gamma A and B for which the stationary state is quasi-stable. Okay, so in order to understand this, if we look at yt is equal to ys plus st, like I said before, this is the steady state or the stationary state or even the equilibrium outcome, and this is a very small change or a very small deviation. And what happens is if deviations fall or shrink, we can see that the equilibrium will be stable because there won't be any deviations. If deviations increases or grows, then we can see that the equilibrium is no longer stable. So equilibrium is unstable. And if deviations don't grow or shrink, then the equilibrium is quasi-stable. So to see how we can see if the equilibrium is stable, unstable, or quasi-stable, we are first going to rewrite one of our difference equations, which was delta t plus 1 minus delta t, which was equal to lambda r s delta t. So this we can rewrite as delta t plus 1 is equal to delta t minus gamma r delta t. If we now factorize out the delta, we have 1 minus gamma r delta t. So now, this is the matrix, if I call this that sort of moves or controls these deviations. So now we have a couple of rules. If the eigenvalues of this matrix M have an absolute value less than 1, deviations shrink and are therefore stable. So that's our first rule. Our second rule is if eigenvalues have absolute value greater than 1, deviations grow, and so is unstable. And lastly, if absolute value of the eigenvalues is equal to 1 but not greater than 1, it is quasi-stable. Some important notes that we have to make is that for this one, all eigenvalues need to be less than 1. For this one, it's any eigenvalue greater than 1, and for this one, it is 1 eigenvalue has to be equal to 1, and then the others shouldn't be greater than 1. So pretty much everything depends on the eigenvalues. Cool. So everything depends on the eigenvalues of the matrix M, which the matrix M is 1 minus lambda R. I'm going to turn this one into the identity matrix. So we have identity matrix. It's only just come to me that there should be a plus, and this should also be a plus, and this should also be a plus. Hopefully you guys spot that mistake before me. Yeah. Okay, going back to this, so now that we have M is equal to I plus gamma R, if we find the eigenvalues of the matrix R, we have to use that of R minus lambda I is equal to 0. So this is the characteristic. So this will give us the characteristic equation. So the matrix R was 1 minus 1 minus 1 minus B 1 0 minus A 0 1. Okay, so we're going to be finding the eigenvalues of R. Okay, to do that we are going to be working out the characteristic equation and equating it to 0. To work out the characteristic equation we do the determinant of R minus lambda I. So that gives us 1 minus lambda minus 1 minus 1 minus B 1 minus lambda 0, and then minus A 0 1 minus lambda. I'm going to be using the last row to find the determinant because I think that would be easiest. So we get minus A minus 1 minus 1 1 minus lambda 0, and then plus 0, and then it doesn't really matter what this matrix is, and then plus 1 minus lambda minus 1 minus B, and then 1 minus lambda over here. Cool. If we start working out the determinants, we get 0 minus 1 plus lambda plus 1 minus lambda brackets 1 minus lambda 1 minus lambda minus B. Cool. If we now expand this out, we get A brackets minus 1 plus lambda plus 1 minus lambda cubed minus B 1 minus lambda, and this is equal to 0. So now we get 1 minus lambda cubed minus b 1 minus lambda plus a minus 1 plus lambda is equal to 0. What I'm going to do, I'm just going to change this bracket by taking out a minus. So this is now going to be minus a, and what's left behind in the bracket would be 1 minus lambda. So now all the brackets are 1 minus lambda, 1 minus lambda, and 1 minus lambda. So what I can say is 1 minus lambda is equal to 0, and then I can divide by 1 minus lambda. So we get one value of lambda is equal to 1, and we are left behind with 1 minus lambda squared minus b minus a is equal to 0. So now I can say 1 minus lambda squared is equal to a plus b, and then 1 minus lambda is equal to square root a plus b plus or minus. So lambda is equal to 1 minus root a plus b, or lambda is equal to 1 plus root a plus b. So those are our 4 eigenvalues. So first one being 1, second one being 1 plus root a plus b, and then the third one being 1 minus root a plus 1 minus root a plus b. So now these are just the eigenvalues of R. We need to find the eigenvalues of M. To do that, the eigenvalues of M, if I call them mu, would just be mu1 plus gamma and the eigenvalues of R, which are lambda. So then we have lambda is equal to 1 plus lambda. Sorry, mu is equal to 1 plus gamma, is what I meant to say. Mu, so this would be mu1. Mu2 would be 1 plus gamma root a plus b. And then finally, mu3 would be 1 minus 1 plus lambda minus lambda root a plus b. Okay, what we can see from these three eigenvalues is that if a plus b is greater than 1, if a and b is greater than 0, then we can say the eigenvalue mu2 is than greater than 1. That means deviations grow and stationary state is unstable. And that is because if any of the eigenvalues are greater than 1, deviations grow and we have an unstable stationary state. So that's that. If we now flip this then, a plus b less than 1 is required for stability. Because if a plus b greater than 1 gives an eigenvalue which is greater than 1, and hence the stationary state is unstable, if we now reverse this, we should have a requirement for stability. So now if a plus b is less than 1, then we should have our first eigenvalue, which was 1 plus mu, the absolute value of this, be less than 1. And we need to have 1 plus mu a plus b, the mod of this, less than 1. And then 1 plus mu minus mu root a plus b, also less than 1. That's because all the eigenvalues have to be less than 1 for the deviations to shrink and to have a stable solution. So now we have this. We need to find the exact value for gamma. So, okay, so if I rewrite this as 1 plus gamma 1 plus root a plus b is less than 1, we get gamma 1 plus root a plus b is less than 0. Hence we get gamma is less than 0. Another way of writing this same modulus would be to say minus 1 minus gamma 1 plus root a plus b is less than 1. Therefore, minus gamma 1 plus root a plus b is equal to, would be equal to 2. And then we would have gamma 1 plus root a plus b is greater than 2. So gamma has to be greater than 2, 1 plus root a plus b. And if we check, we can find that these two also fit with these other two conditions. So we have minus 2, 1 plus root a plus b, and then and then gamma, and less than 0. So this is the condition for gamma which is needed for stability. So we have a stable equilibrium if and only if we have a plus b is less than 1 and minus 2 over 1 plus root a plus b lambda is greater than that but less than 0 gamma. Cool. So now looking at quasi-stable. So from before, this required at least one eigenvalue that has the mod of it equaling to 1, but none can be greater than 1. So because none of them can be greater than 1, we still have the condition where a plus b is less than 1. And now, if we look at those same conditions, we can't have them greater than 1. So 1 plus y has to be less than or equal to 1. 1 plus mu 1 plus root alpha plus b less than or equal to 1. And then the mod of 1 plus mu 1 minus root a plus b is less than or equal to 1. Okay, so if we now solve this, we have 1 plus mu 1 plus root a plus b is less than or equal to 1, which gives us mu is less than or equal to 0. If we solve for minus 1 minus mu 1 plus root a plus b less than or equal to 1, we get minus mu 1 plus root a plus b less than or equal to 2, which we can write as y is greater than or equal to minus 2 divided by 1 plus root a plus b. So now we want at least one eigenvalue to be equal to 1. So what I'm going to say is gamma is equal to minus 2, 1 plus root a plus b. So what that now does is it will make this one equal to 1, and these two conditions will still be met. So for a quasi-stable equilibrium, we will have a plus b is less than 1 and y is equal to minus 2 over 1 plus root a plus b. Okay, so that is part C done. Hopefully that made sense. Moving on to 18. Okay. Consider the function f of x y is equal to x plus 2y and the constraint optimization problem, which is the maximum of the function x of y subject to x squared plus 1 over b y squared is equal to 1. Write down the Lagrangian for this constraint optimization problem and the first order conditions. So we have x plus 2y plus lambda x squared plus 1 over b y squared minus 1. If I first differentiate partially with respect to x, I get 1 plus 2x lambda is equal to 0. Partially differentiating with respect to y, I get 2 plus 2 over b y lambda is equal to 0. And partially differentiating with respect to lambda, I get the constraint, which is x squared plus 1 over b y squared minus 1 is equal to 0. So that's part A. Part B, find the local optimum. That means I'm going to have to solve these first order conditions. I'll do it over here just to make it a bit easier to see the first order conditions. If I rearrange this first one to make lambda the subject, we get lambda is equal to 1 over 2x minus 1. And rearranging the second one again with respect to lambda, we have lambda is equal to minus 2 over 2 over b y, which is the same as writing minus b over y. If we now equate these two together, we have minus 1 over 2x is equal to 1 over minus b over y. We can change these both into pluses. So then we get 2x is equal to y over b, and therefore x is equal to y over 2b. If we now substitute this into our third equation, which is the constraint, we get y squared over 4b squared plus 1 over by squared is equal to 1. So factorizing out the y squared, we have y squared brackets 1 over 4b squared plus 1 over b is equal to 1. If I times this top and bottom by b, I get b and then b squared. And then if I times it by 4, the top and the bottom, I get 4b over 4b squared. Now we can add these two, which gives me, if I write it over here, y squared brackets 4b plus 1 over 4b squared is equal to 1. So then y is equal to, y squared is equal to 4b squared over 4b plus 1. So y is equal to plus or minus 2b over root 4b plus 1. So y is equal to 2b over root 4b plus 1, or minus 2b over root 4b plus 1. If we now work out the x values, x is equal to y divided by 2b. So we would get 1 over root 4b plus 1 over here, because the 2b just goes. And over here we get minus 1 over root 4b plus 1. Now to find the values of lambda. Lambda is equal to minus 1 over 2x. So that means lambda is equal to minus 1 over 2 over root 4b plus 1, which can be written as minus 4b plus 1 square rooted all over 2, and over here it will be positive 4b plus 1 over 2. Cool, hopefully that made sense. Calculate the bordered Hessian, sketch the constraint and the relevant indifference curves, and identify whether there is a local maximum. All right, so bordered Hessian is 0, and then the first derivatives of the constraint in the first row and the first column, and then it is the normal Hessian of the Lagrangian. Cool. So if we work this out, we have 0, first derivative with respect to x partially is 2x, then it is 2 over by. That's the same over here. The second derivatives of the Lagrangian is 2 lambda 0, 0, 2 over b lambda. Now if I work out the determinant of the bordered Hessian, we get 0 minus 2x, 2x, 0, 2x, 2 over b lambda. This is also 2 over b, y, plus 2 over b, y, 2x, 2 lambda, 2 over b, y, 0. So of course this just turns into a 0, and we get minus 2x, 4 over b lambda x, plus 2 over b y, minus 4 over b lambda y, and then we get minus 8 over b lambda x squared minus 8 over b squared lambda y squared, which is minus 8 over lambda b squared bx squared plus y squared. As that, a cool little trick that we can do is x squared plus 1 over by squared is equal to 1. This is the constraint. If we times this constraint by b, we have bx squared plus y squared is equal to b. This and this is the same. So we have minus 8 lambda b squared multiplied by b, which is just minus 8 lambda over b. So now, if we look at solution number 1, which was 1 over root 1 plus 4b, 2b, root 1 plus 4b, and then minus 1 plus 4b, 2. So this is x, y, and then lambda. If I use this equation of the determinant, we get 4 root 1 plus 4b all over b squared brackets b over 1 plus 4b plus 4b squared over 1 plus 4b. As you can tell, this is going to be greater than 0, as the det of the bordered Hessian is greater than 0, we have a local maximum. If we now look at solution number 2, which was negative 1 over root 1 plus 4b, and negative 2b over 1 plus 4b, and then root 1 plus 4b over 2. This time if I use this, we have minus 8 lambda b, which is minus 8 times 1 plus 4b over 2 over b. And we can see that this will be negative. So it'll be less than 0. So as the determinant of the ordered Hessian is less than 0, we have a local minimum. So solution 1 was a maximum. This was a minimum. Cool. Hopefully that made sense.